Alright guys, this is 7.4, rational functions and their graphs. Now, this lesson it probably has the most information out of any lesson for the entire year. There's a lot of rules that go into graphing these things. So when we do this first one, it's going to take a while to do just one example. Really going to break it down for you guys and show you how you do step-by-step graphing these things. Alright, remember, chapter 7 is all about rational expressions. So now we're just going to practice graphing when they are being divided. Alright, a rational function is of the form y equals f of x over g of x, where f of x and g of x are polynomials. I'm going to highlight just some key things I want you guys to remember. Okay, a rational function, it can have both a vertical and horizontal asymptote. Right, it doesn't have to, but it can have both. It can also have a third one, which we're going to see, called an oblique asymptote, but don't worry about that for right now. A rational function has branches. Think back to reciprocal functions. Those always had those two branches that made a hyperbola. For rational functions, you're going to have one more branch than the number of vertical asymptotes. So if we have 2 vertical asymptotes, there's 3 branches. 4 vertical asymptotes, 5 branches. Okay, graphs of rational functions can be continuous, which means there are no jumps, breaks, or holes, or discontinuous. There are 2 types of discontinuities that occur. You've seen one of them already. A non-removable discontinuity. These are the ones that we've seen. These are the asymptotes, okay? And we cannot remove those from the equation, is what that means. Removable discontinuities, which come up a lot in pre-calculus, a lot in calculus, or are also called holes. Those occur when a factor cancels. I showed you guys this earlier in the year and said we'll be looking at these later on, but they're something that can be a discontinuity that can be removed from the equation. Alright, so first thing we're going to do is how do we identify holes, how do we identify vertical asymptotes, okay, because we need to know where those are on our graph. Let's look down at number 1 here. Finding vertical asymptotes. Okay, what we are going to do, the first step in these problems are going to be to factor your numerators and denominators. So nothing can happen with my numerator here. My denominator, difference of 2 squares. The x minus 3's cancel out. You're left with 1 over x plus 3. Now, we should know by now that this means that there's going to be a vertical asymptote at x equals -3, because I cannot have my denominator equaling 0. Okay, so just set your denominator equal to 0 and solve. That's how you figure out your vertical asymptotes. Now, this x minus 3, because it is a discontinuity that gets canceled out, right? Like right here in this equation, or the original, if I plug in +3, I'm going to get 0 in my denominator, which would make you think it's a vertical asymptote. But because I can cancel it out, we call it a removable discontinuity. We're removing the discontinuity from the equation, or we call it a hole. We say that there is a hole at x equals +3. Alright, you guys try to do these 3 right now. Identify vertical asymptotes or holes, if there are any, by first factoring. Okay, I'm going to do the work here. You don't need to pause the video. You should try to do it on your own though. Okay, first step, factor. If nothing can be canceled out, then there are no holes. Just got to see where the vertical asymptotes are. Okay, no factoring can be done in number 3. So we just say there's a vertical asymptote at x equals -2. Again, for the vertical asymptotes, I'm checking my denominators. I want to see where do my denominators equal 0. And for number 4, no factoring can be done, so I want to think x squared plus 2 equals 0. The only types of numbers we're going to get are imaginary, because I would take square root here. I can't have square root of a negative number. So we have no vertical asymptotes. We're graphing in the real plane, so we don't care about imaginary. All right, number 1 is probably your best example to look back at because this had a vertical asymptote and a hole. 2 and 3, no holes. So that's vertical asymptotes and removable discontinuities. Next step is we got to figure out are there horizontal asymptotes. The way you tell if there are horizontal asymptotes or not and where they occur is by looking at the degree. We want to compare the degree of the numerator and the denominator. Okay, what do I mean by degree? Let's take a look at this first one here, and there are 3 different cases. When I say I'm looking at the degree, I want to think to myself, what is the highest exponent in my numerator? What is the highest exponent in my denominator? Okay, here the numerator's exponent equals 1. The denominator's exponent equals 2. So this is a case where n is less than d. And when your numerator's degree is less than your denominator's degree, you'll have a horizontal asymptote at y equals 0. So 1 is less than 2. Okay, and I'm looking at these numbers here. 1 is less than 2. That means I have a horizontal asymptote at y equals 0. Here's another example. The degree of my numerator is 2. Denominator is 3. 2 is less than 3. That means I'm going to have a horizontal asymptote at y equals 0. That's case 1. And you're never going to have more than one horizontal asymptote in an equation. Case 2. Denominator and numerator have the same degree. If that is the case, then you want to look at the leading coefficients of the numerator and the denominator. That'll tell you where your asymptotes, your horizontal asymptotes happen. Let's take a look here. This is x to the 1. The degree here is 1. 1 equals 1. So I want to look at the leading coefficients of each of these, of the numerator and denominator. This is 1, this is 1. So my horizontal asymptote will happen at 1 over 1, which equals 1. Numerator's degree is 2, denominator's is 2. Take a look at your leading coefficients. Numerator's is 4, denominator's is 2. Okay, because they have the same degree, my horizontal asymptote is going to happen at the numerator's coefficient divided by the denominators, or y equals 2 in this case. Case 3 is when the numerators is greater than the denominators. When that happens, that's the easiest one. No horizontal asymptote. X squared, x to the 1, we're not going to have any horizontal asymptote because 2 is greater than 1. Numerator's degree is 5, denominator's is 2. 5 is greater than 2. We're not going to have a horizontal asymptote. And down here is just a little silly sayings to help you remember. If you're big on top, just stop, because there ain't no horizontal asymptote. So if your numerator is bigger than your denominator, no horizontal asymptotes. Alright, if the bottom is heavy, the line is steady at y equals 0. Just some silly sayings to try to help you figure it out. Okay, so that's vertical, horizontal asymptotes, and holes. This next part is a little new. Oblique asymptotes. Oblique asymptotes are asymptotes that are not vertical or horizontal. They might be along a line that's slanted like this, okay? Now, there's a very specific case when these obliques come up. The degree of the numerator has to be exactly one more than the denominator. So what does that look like? It has to be like x cubed over x squared plus 1. Or 3x to the 5th divided by 2x to the 4. Okay? Numerator's degree is exactly 1 greater than the denominator. Then there's going to be an oblique asymptote. To find it, you're going to divide the numerator by the denominator, and the quotient that you get is the equation of the oblique. Alright, so let's just take this second example here. Alright, 3x to the 5th divided by x to the 4th. When I go to simplify this, I get 3/2 x. That would mean that I have an oblique asymptote at y equals 3/2 x, that line. So I'd have to graph this line using the slope, the intercept, draw a dotted line at that point. Okay, oblique asymptote at y equals 3/2 x. Okay. Now, I know that sounds like a lot, and it's a lot of rules to remember, but I really broke down the steps for you guys right here on how it's going to work. All right, and we're just going to take it one step at a time right now. Okay, step 1. Always start by factoring the numerator and denominator if possible. Because you want to see if stuff can be canceled out. You want to see where the vertical asymptotes are or if there's holes. Numerator stays, denominator becomes x minus 3, x plus 1. Now, nothing can cancel, so we are done with step 1. Step 2. Find any holes, plot them as open circles. Okay, now every time I do these problems, I'm going to make a list down the left side. First thing I'm looking for is holes. There are none. Second thing I'm looking for, vertical asymptotes. Look at the factored equation. Vertical asymptotes are going to happen where the denominator is 0. That happens at x equals 3 and x equals -1. Okay, let's plot those vertical asymptotes. Make sure you make your asymptotes dotted lines. Right. Step 4. Find horizontal asymptotes, if any. And just another thing I like to add in here is the number of branches. Remember from page 1, the number of branches you're going to have is 1 more than the number of asymptotes. Think about these asymptotes cutting your graph into sections. There needs to be a branch in each of the sections. So there are going to be 3 branches here. 1 in this left section, the middle, and then the right. Okay, step 4, horizontal asymptotes. You got to go back to page 1 and look at the rules there. Think about which one of the 3 cases we are looking at. All right, and to do that, it's easiest to just look back at your original before you factored. This has a degree of 1. This has a degree of 2. Numerator is less than the denominator. That means we have a horizontal at y equals 0. Let's plot that. Now, look back at the oblique asymptotes. Forgot to underline this. You cannot have a horizontal and an oblique or slant asymptote. So once I know I have a horizontal, I know I have no obliques. Step 5, find the y-intercept, because I want to start getting some points to plot so I know where my branches go through. Do that by setting x equal to 0. When I plug 0 into my function, and you want to use your factored function, okay? Everything I'm going to use is for this. Plug 0 in, I'm going to get 0. All right, I'm not going to show all the work there, but you would do the calculation when you plug in. When you plug in 0 for x. Step 6, find the x-intercepts. And the way you find the x-intercepts is by setting the numerator equal to 0 and solving for x. So this one's pretty easy, because you're just going to do 0 equals x, and obviously that's your final answer then. Okay, so I'm plugging in 0 for y, I get 0 out for x. So our x-intercept is the y-intercept. There's no others. And now the next step is a little weird, okay? It says that the graph is we have to determine if the graph will intersect its horizontal or slant. Think back to yesterday. You wrote down for horizontal asymptotes that you can cross them, but you can't cross verticals. So we have to check, do we cross our horizontal asymptote? All right, and the way that we check to see if we cross is we take our asymptote, so y equals 0, and we set it equal to our function. And we check and see, does my function, can I solve this? Does my function have an x value that it does cross there? It does. Okay, it crosses at x equals 0. And hopefully you realize that when you plotted your intercept, that I was on the horizontal asymptote. So it does cross the horizontal asymptote at x equals 0. Okay, now, that's important because I know that it's not going to cross anywhere else. Otherwise, it would have just came up. So the last thing we got to do is just pick some points in each of the 3 sections, just so we have an idea of what this graph looks like. And you'll have a calculator to do this. So I'm going to plug in -2, and I'm going to plug in, again, to this factored one, this factored function, not your original. Plug in -2, I'm going to get -0.4. Okay, plot that point, 1, 2. Now I know that I don't cross this horizontal or this vertical, so my function's going to have to look something like this. I don't even need another point in that section. That's enough. Okay, the middle section now. So I have a point at 0 already. Let's pick a point at 1. I'm going to get -0.25. Let's plug in 2. I'm going to get about -0.7. Okay, and it looks like this thing is going to come like this. And if you plug in a point just to the left of 3, you'll see that it shoots down. Okay, and it actually looks like a cubic function. That takes care of our middle section. Last one is a section to the right. Plug in 4, you get 0.8. And I'm picking these numbers for my x based on my asymptotes. I want to make sure I'm in each of the sections between the asymptotes. So 4, I get 0.8. I know it needs to go along these asymptotes, so we are done there. Okay, domain, range. Domain's usually pretty straightforward. You just have to take out your vertical asymptotes, and you might have to take out holes if they're in there, so just be careful with that. Now range. Range, you cannot just look at your horizontal asymptote and take out 0, because my range, I actually do hit 0 here. So you have to just work your way from bottom to top. See if you hit all of the points in between. Okay, I'm going to go down to infinity. This cubic is going to hit all real numbers here. So my range here is all real numbers. That's it for number 1. A lot going on. I know that took a while, but I really wanted to break down all the steps for you. Make sure you guys are filling out a table that looks exactly like this on the left side, to help you stay organized and fill in the points. Okay, get your vertical asymptotes plotted, figure out your holes, figure out do you have a horizontal or oblique asymptote, get your intercepts, see if it crosses those asymptotes, and then pick points in each section so that you have an idea of what the graph looks like. Alright, I'm going to jump to, let's see. I'm going to jump to number 2. Number 2 is kind of a weird one. Okay, number 2. First step should be factor. Okay, difference of squares up top. We have a GCF of 3 on the bottom. And we get x plus 2 over 3 because the x minus 2's cancel. That's important, right? We know now that when anything cancels out, that tells me that there's going to be a hole at the point. Okay, there's going to be a hole at x is 2 because 2, when I plug in 2, that's when I would get 0. Okay, and I'm going to take 2, I'm going to substitute it in to this function here, the simplified one. That would be 2 plus 2 over 3, which gives me 4/3. I'm going to go put a hole there now, just so I don't forget later on. So 2 and 4/3. Okay, next thing I should look for, vertical asymptotes. Look at your ending function, there's going to be none here. It's good to know the number of branches you're going to have. If I have no vertical asymptotes, that means I'm going to have 1 branch. And now I got to figure out, do I have a horizontal or do I have an oblique asymptote? Look back at your degrees of your numerator and denominator. Numerator is greater than denominator, so there's going to be no horizontal asymptotes. Okay, because 2 is greater than 1. And now I just got to ask myself, is this the case where I have an oblique? Yes, it is. This is an oblique problem. Because 2 is exactly 1 greater than 1. So, how do I find an oblique? Go back to page 2. And the way you find an oblique is you're going to divide the numerator of your original by the denominator of the original. Okay? Now, how do we do that? We are going to have to do long division. Okay? Anytime you have an oblique, you have to do long division. So my denominator, 3x minus 6. Again, everything I'm doing right here, this should be minus 4. Is just to find my oblique. Alright, I want to think 3x times what will give me x squared? 1/3 x. Distribute this 1/3 x to 3x, and to negative 6, I get x squared minus 2x. I want to subtract this line. Okay, remember, if you do this correctly, this first set should cancel. Here you're left with positive 2x minus 4. Now I want to think 3x times what will give me 2x? That is plus 2/3. Distribute that 2/3. You'll get 2x minus 4. We're going to subtract that line again. And we get 0, which is great. When you do your long division, whatever answer you get here is going to be the equation of your oblique asymptote. So my oblique asymptote is y equals 1/3 x plus 2/3. Okay, let's go and plot the oblique asymptote. So it has a y-intercept at 2/3. And I'm going to go up 1 over 3. Up 1 over 3. Next step, y-intercept. Plug in 0 for x, I would get 2/3. Okay, I'm going to go plot that point. So 0, 2/3 falls right on the oblique asymptote, so that's important to remember for later. The x-intercept, I'm going to plug in y is 0. Okay, and I solve. When I do y is 0, okay, I'm going to solve this equation here. I'm going to get x equals negative 2. So I have a x-intercept at negative 2, 0. 2. Okay. If you graphed it properly, it should also look like it falls right on the oblique asymptote. And now we got to ask ourselves, do we cross the oblique at any point? Just like with the horizontal asymptotes, we took the horizontal asymptote, we're going to take the oblique, and we're going to set it equal to our simplified function. So I'm doing 1/3 x plus 2/3, and I want to see where does it equal x plus 2 over 3. Now remember, I said this was a weird problem, right? These all have a denominator of 3, so the 3's can go away. We have x plus 2 equals x plus 2. When you have the left side and the right are exactly the same, that means there are infinitely many solutions. So it crosses the oblique, yes it does, and it crosses it at every single point. This, our final solution, is actually the oblique asymptote itself. So you can fill in the oblique except for the hole. Leave this hole open, and that's our final answer. Okay, a little weird. This doesn't always happen with obliques, but I showed you this one specifically because it does. Alright, you might do this and it might not cross, and then you'd have to draw in your branches. But this one, the oblique actually is your function. Okay, domain. It's going to go to negative infinity. At x equals 2, I have a hole, so take 2 out of your domain. For range, it goes down to negative infinity. It jumps at 4/3 at the hole, so take 4/3 out of your range. That's really the only weird one. 4 is a little tricky too, how it works. But 3 is pretty straightforward. Just use your rules properly. Make sure you factor. 5 gets a little bit difficult with the computations. Just be careful. Make sure you're doing every step how you should be. And as long as you follow those steps, you guys should be fine. Okay? I want you guys to finish this now for the rest of the time.